but the better name would be differential privacy for dummies, because I'm complete dummy myself in this topic, and I make the slides so that I can understand what I'm talking about while I'm giving presentation. So if it seems too simple and naive to you, just tell me. We can immediately jump to the last slide.
That's precisely the principle of the reading group.
Okay, that's great. So this presentation is made after 3 main sources. So I list the foundational work of Cynthia's work as the last one, because I didn't borrow a lot of material from there, but it's the principal work in this on this topic and seminal, I would say. And I mostly present this interaction from 2 sources dedicated to differential privacy. One is the general interaction, another one is a little bit more connected to machine learning and especially to applications in deep learning. So the generic introduction would be to motivate why do we even want to consider the data. You know that data can be used for training some models. The more data is collected, and now we collect a lot of data, the more we want to protect privacy. And right now, with a lot of data in use, it's a good idea to employ some a little bit more developed techniques of privacy, as we used to deploy before, and differential privacy is one of them. But it's a generic introduction, just to give an overview of what I'm talking about. Maybe it would be a good idea to mention it, that differential privacy, even though it was introduced in 2006, it hasn't been used for quite a while until recently, and now big companies that have the means to do so, like Google, Apple, they employ this technique. So what was before? What was here before? Early approach to privacy. The most naive way to what you want to do is to anonymize the data. You collect some data, you delete some private information as a name, address, and you just leave only the relevant information. Here, you don't need to read this text, please. It's just an extract from the article, and I want to show the excitement of the author of the article with boom here, that it's quite easy to identify the person based on just 3 values. 87% of all Americans could be uniquely identified by only zip code, birth date, and their sex. And the same happened to the governor of Massachusetts when they published personal medical data without names, etc. And the governor was easily identified by a graduate student. A little bit more developed approach would be k-anonymity, which basically means that in the data there should be at least k-1 additional, at least k additional records, at least k records of the same type. For example, here, what I mean by the same type, okay, maybe, yeah, I forgot. I'm sitting just because of this. So here, the idea is that zip, age, and nationality are the same for these 4 entries, as well as here and here. And this table is then for anonymous, because there are 4 entries for each identifier. This is that's a decent approach to privacy. Unfortunately, it's not the best, because you can employ it only when you have not a lot of entries. The more columns for the table you have, the easier it is to identify the person. Or if you employ k-anonymity in the table with a lot of columns, with a lot of entries, then you will lose all the information, because you will just delete the necessary information for the for your task. And that's the usual problem in privacy literature. You want to achieve some trade-off between usability of information and privacy. And there is a theorem that it's impossible to achieve perfect privacy without losing all the usability of the data. And but we can speak about approximate terms. And approximate terms would be how much privacy can you afford yourself to lose. So, and it's a good idea to be able first to quantify it. And second, it's a good idea to introduce some a technique that will allow you to use the data simultaneously, allowing you to have some privacy guarantees. And that's a differential privacy. And the intuition for it is usually given like this. The main idea of the differential privacy is that for an adversary or an attacker who wants to know something about you, there shouldn't be a lot of difference in the data set, whether you are in or not in this data set. Basically, which will mean that if you decide to be included in the data set, then you have some guarantees that it won't change much, and your privacy won't be leaked so the chance of privacy violation is small. And here the magic represents the differential private mechanism. I will explain in details what it is, but the idea, just the intuition, sorry, the idea of the intuition is that you apply differential private mechanism to a data set, and you apply differential private mechanism to another data set. And basically the same doesn't mean that they are the same, but the likelihood of obtaining the same outcome is high. I hope, but we will get to more details after. So why is it good? Why is it nice to have differential privacy? It has a lot of nice and cool and interesting properties. So it can protect any kind of information you want to protect. It doesn't matter what the information is as long as you can code it. It works no matter what the adversary knows about the data. So it can be the case that, for example, adversary knows everyone in the data set except you. It might be the case that adversary has an auxiliary information. It might be all the other case, but you don't need to care about that, because what you want to care about is that you don't even need to care about that. Second nice property is that we can quantify the privacy loss. For example, if we consider key anonymity, number key doesn't tell you a lot about your privacy. So it doesn't quantify privacy. The only thing that you know is that the bigger key, the better for privacy, because there are k minus one same entries as you. But it doesn't quantify what happens. It doesn't tell you what happens when the database is leaked and when your privacy is compromised. So here it's much clearer. You have corresponding parameters, so epsilon, and differential privacy is usually either epsilon differential privacy, either epsilon delta differential privacy. We will focus on the former one. And if you have some particular value of epsilon, you can say what is the increase of information of the adversary about you based on this value. And two very important properties that allow us to use differential privacy in the for the learning, for the machine learning, for the deep learning is post-processing and composition. What does it mean? It means that post-processing any mechanism updated to differentially private output. So when you have some database, you have that differential privacy mechanism, you gain some statistic out of the data. Statistics can be anything. Any function applied to this statistic will also be differential private, because it's guaranteed. Composition is a nice property, is that you can compose several differential private mechanisms, and it will still be differential private, a little bit less differential private. For example, yes.
I don't understand the statement. Suppose epsilon is 1.1, then we can say the attacker who thinks that target intercept is 50%. Can increase their level of certainty. I don't understand how you compare.
Yes, it was
50%.
Yes, of course. We will move to the numbers a little bit later. It was just to illustrate that you can make precise statements. Okay. Sorry for the confusion. Just that you can quantify those information. And composition is a nice property because, for example, for K anonymity, it doesn't hold. If you have Alice and Bob who both made requests to the database for different purposes, then they gain different statistics out of this. And then by combining these two, they can, the combination won't be K anonymous. it might even reveal the full information. Data differential privacy is protected from that, and unfortunately not fully, but it can give you guarantees. So I will just make a little bit of spoiler. The combination of k, the composition of k differential private outcomes is k epsilon differentially private. So what is epsilon? What is differentially private, and what is the mechanism itself? So it's a formal definition in which we consider two data sets that differ at most by one entry. And we apply some mechanism, some randomized mechanism to be more precise, and we obtain some output of this mechanism. This output could be basically anything. For example, you have a data set and you made a query there and asking how many people in the data set have blue eyes. We will have this example later. Or you can make several queries about males younger than 35 with a job. I don't know, anything. The query, the output of the mechanism could be anything you want. The idea is that you want to make it private. You want that an adversary who makes a query to the database doesn't gain additional information, even if this adversary has another information like Michael Brown has blue eyes, and he wants to know if Michael Brown is in this data set. So, what is the formal definition? That this mechanism is the mechanism that gives an outcome, the query, the response to the query is epsilon differentially private if basically, I will translate it a little bit, if for all the responses the probability of obtaining a particular response from the set D is not very far from probability of obtaining the same response for data set D prime, which is quite a strict definition, because if here it is written that these two databases differ only by single record. So if an adversary wants to know that whether Michael Brown is in the dataset or not, and we have two datasets where Michael Brown is, and another dataset where Michael Brown is not, then the probability of obtaining the same response to the query of the adversary, they shouldn't be too far away from each other. And how far away they are is measured exactly by the parameter epsilon, which we take exponential law. So that's yes.
So D and D prime are symmetrical. So you also that.
Yes, exactly, exactly.
That L,
exactly.
L even D is D prime is bounded.
Yes, exactly.
It's why your epsilon is more than one. Right?
Yes, exactly.
Okay.
That's but it doesn't need to be more than one, to be honest. But
for example,
yeah, if my example is close, yes, but
in fact, what you say, it must be greater or equal to 0 because you have the
yes, exactly. If the condition is that it should be positive.
But
if you have epsilon equals 0, you have the equality.
Okay.
It is because of the exponential function.
Okay.
Yes.
Right.
So
I have the same question as you.
Indeed, they are symmetrical, so you can rewrite the definition.
Okay, so in practice, what you will record on your servers is the result of operation M instead of the source data of D.
Yes.
Okay.
That in practice, that's a good question, because in practice there are basically two main ways to implement differential privacy: centralized and local. Centralized is when agents report their data to a centralized operator,
Okay.
and then this centralized operator outputs a differentially private M of what this operator obtains, and local differential privacy, where each agent first employs M on their data, and then reports it to the database. These are two a little bit different approaches. They differ in in some things.
Okay, and in that case, you need your M to have a particular structure that allows you to
yes, exactly.
decentralize the computation in some sense.
Yes, imagine that you how Apple does it, at least how they claim they do it, because we can check. But they claim that computation happens on your smartphone, so you do not report your data. It is first being preprocessed by some differential derived mechanism, and then it's being sent to the databases. So yes.
There's one thing I don't get. I mean, so there ought to be some properties on M, because I mean, if M is asking the question, is François Durand part of this list? So if I remove François Durand from the list, right? So how can I be absolutely, how can we satisfy these equations? I mean, it will be yes or no in one case, and 0 in one case, 1 in the other. So you need assumptions on M.
That's a good question, and Hans saying we will just move to the example. But imagine if you have a database, and with the list and where you have all the entries, and for example, François Durand is one of them, right? And the query is whether François Durand is not on this database. You give randomized output. You take, for example, you throw a coin, and with the probability 1/2, you say yes. For the probability 1/2, you say no. We'll give an information to adversary who wants to know. If it won't give any additional information because you just randomly answered.
Okay, so it's a property of M.
Yes.
We want to restrict the set of queries
exactly
in such a way that although François is in the you cannot. I mean, you will randomization is
exactly
is a way of implementing the
exactly, and that's the next, and that's the next slide. Yes, exactly. No, that's a good question, because that's the flow of the presentation, and that's how I prepared. So,
and I guess that in the case that you mentioned, it's it's not epsilon dp for any epsilon.
Yep.
Yeah. Yes, exactly. Okay. It will be epsilon dp, and in your example, the usability of the data then will be quite low, because if you want to know where the François Durand is in data for your learning, it won't help. Okay. But the price will be.
So the principle is to restrict the set of queries in such a way that the property is by randomization. M is your query in sense. You want to restrict queries to be such that this property is satisfied.
Yes, yes, exactly. But I wouldn't say that it's a restriction. It's more for just of frustration of your queries. You do not restrict the type of the query, for example, but you add a lot of noise, for example, or not a lot of noise. It depends on the query itself. But so the mechanism in general with hand waving is that there is some deterministic query, and then you randomize the response to this query. And it can give.
Excuse me, I think that in fact, François' question is related to mine, in the sense that should I envision the process M as the set of queries that are authorized to the database, or, and that was what I understood in the first place, or should it be envisioned as a preliminary transformation that you do on your database before recording it, and essentially you erase the original D because you don't want to have access to the full information. Do you see what I mean?
Yeah, I see what you mean. But like I said, it depends. Indeed, for every query that you can have, you can guarantee some differential privacy. But of course, it depends on the query. For example, if the query is give me the whole database, then boom, you will have to add a lot of noise in the database, and yeah, and it won't give you any useful information. So the example is first I from the definition in a little bit simpler terms, so that it's obvious what we are doing, and then I give an example where we have some numbers already, and that's where we have epsilon 1.1 in this example. Basically, imagine that you making a survey. are you doing some illegal activities? And you can throw a coin with probability 50, your respondents will say truth. And the answer will be yes with probability 50, they will answer at random. And then you have these probabilities of obtaining responses. And if you want to make these probabilities equal, so the lower bound of the epsilon would be 1.1 because epsilon exponential time in power epsilon would be 3 here. So
so what is the query? What is the randomization? Is the answer to the query, right?
yes,
right?
yes.
So what is the query? What is the randomization?
Yes. So here you can basically you collect database in a way that any query will be differentially private. So here you collect the database in the sense because the answers that your respondents tell you, they already learned because they throw a coin. So basically, it's the same as local differential privacy, because agents, they blur their information, which you then collect to the database as a survey. And here you can guarantee this property by with the epsilon equals 1.1, just because of the probabilities that I listed. So the probability of obtaining.
So if I understand well, for example, let's imagine that Apple is doing a survey to know if we have criminal activities.
Yes.
Then I will answer to my computer sincerely.
Yes.
And just before sending my answer to the cloud, with probability 1/2, we just send my answer without modification. And with probability 1/2, it will switch it.
Exactly.
Essentially, so something like that.
Yes, exactly. And then because the probability of
with probability 1/2 it will so with 4 quarters if it's 1/2 is not interesting, but three quarters it will send my answer, and with the probability 1/4 it will send the opposite answer.
Okay, so it's not that the answer to the query is
the initial recording in the database.
So that when people make the query, the effective answer to this query will be blurred automatically.
Yeah.
Exactly.
So you cannot have certain information about me, but you can recover the global percentage of criminal activities in the population.
Yes, and this corresponds to local.
By the rules. Assuming that you know the.
What is the probability that you know yourself?
But the idea indeed, and that's a local differential privacy, because exactly like I said before, you do it on a computer. And then you send
the true information is recorded nowhere.
Yes, and in order to make these probabilities, so these probabilities on top to be equal, we have to assume that E times epsilon is equal to 3, which it says 1.1. So that's the number from the flow. So another intuition from the adversary perspective. Imagine that we output this AD to the attacker, and adversary makes a query to our database. We output A of our database. So apply differential privacy mechanism. And usually in the examples of differential privacy, we always consider they want to figure out whether someone, their target, their interesting figure, is in this database. And we assume the situation when they know everything, so all the information about others except their target. And so for them, there are two possible variations of the data set. Whether their target is in the data set, either their target is not. And they have their initial suspicion. So the probability of their target being in the data set. And then they make a query and update their information given the query, given the response of the mechanism. And this plot here gives as how much they can update their information for epsilon equals, if I'm not mistaken, 1.1. So they can be a little bit more sure, or they can even be less sure. So these are the bounds, the theoretical bounds on their updates. And these are theoretical bounds on their updates based on different values of epsilon. So when epsilon is high, for example, epsilon is 7, they can give from being almost zero certainty to 1, to almost 1. So big epsilon leads to big information leakage. So usually you want to keep epsilon small, but not super small, not close to 0, because you also want to use your data. So this is, I hope it's clear, and we will use this example. So here's the proof. Maybe I will skip it because we don't have that much time. But the interesting notion to understand what's happening with the differential privacy is privacy loss random variable. Basically, if we rewrite the definition of the differential privacy using updated file information, what we want to have is that I will explain here. So having an output O to our query, to the database, we have two hypotheses. Either this database is D1, either this database is D2. We can imagine then again this example whether target is in the database or not, but it can be different. So we want to bound this value by exponential times the power epsilon times the same value, but without additional information. So basically, what does it mean here? That after we update information, the update shouldn't be too large. If you increase epsilon, then it can be large. If you decrease epsilon, then it shouldn't be. It should be small. Then we define the corresponding random variable to this to this quantity. So basically, we just divide by the right part. And why it's random variable? Because the outputs of random mechanisms are random. Yes.
So the first inequality is something that you wish or something that you deduce from the earlier steps?
It's something that you have from the definition of differential privacy.
Okay, so
it's something that we wish. It's something that we wish. Yeah. So assume that A is differential private. We can say it like this, or assume that we want to have differential privacy. Then what would be the bounds on the random variable? Yes.
I understand that the first formula when on the right, the two value of the probability are 1/2, which was what you explained at the beginning.
Yes.
But why is it still valid when I do not understand why we have this formula if the two probabilities are different? I don't. When you define in one of your previous slides, when you define epsilon, this one, so you divide by the probability on the right, and then you get the formula that you give in the new slide.
Yes.
Having 1/2 and 1/2. My question is, it's
basically
go there. Okay.
Yes.
So I will write it.
Yes, I don't know if we have time for that, but it basically follows. Okay. It basically follows from the Bayesian rule.
Okay. So. I believe you understand.
Thank you. But quickly, indeed, we can super quickly. We can write this probability like this, given the conditional probability. Then we can divide everything by this. We can divide anything by this quantity here, and probability rewriting this probability as this one. And then from the definition, we have this particular relation. Okay. And so basically, it's a combination of Bayesian rule and not even Bayesian rule, just conditional probability and the definition of epsilon privacy. But the important thing here, I wanted to give more of an intuition than the derivation, but the derivation is on the previous slide, yes. And so we have some conditional probability that we can bound into the definition of differential privacy. Then introduce a random variable that can be reformulated using Bayesian rule. And then it would be just a probability of the query will equal O for two data sets. And this is called privacy loss random variable. Why? Because it determines how much you can update to your information with the outcome of the mechanism equals O here. And our definition of differential privacy gives us that this quantity is always less than epsilon. So the leakage of your information privacy loss would be always less than epsilon. And here it can remind you some particular quantity. It can this value can remind you some divergence between distributions. And that's exactly what we will see later, but I won't maybe put a lot of emphasis on that, but I want to give an intuition. Why did I even introduce the privacy loss variable? So returning to our example with the number of people with blue eyes on the data set, the query would be, what is the number? The true value is 1000, and the adversary hesitates between two data sets, whether it's 1000 and 1001. The attacker doesn't know which data set is correct. And for two data sets that differ only by one value, we what do we give as an answer, as a response to the query? We give a number obfuscated, noise, biased by some Laplacian noise. So noise from Laplacian distribution. So this is the real one. This is the fake one with the one additional entry. And assume that attacker doesn't know which data set is correct. So attacker puts equal probability on each data set being correct. Yes?
You add this noise to what? To the number?
To the number, the
total number.
Total number, yes.
So you,
Yes. And you might ask how the number can be continuous and real and why isn't, but you can always just take the closest. Yeah. And assume that there are three outputs that an attacker receives. So three situations, makes three queries, or O1, O2, and O3. So if there is an output is O1, then it's more probable to have this output if the distribution is with the mean 1000. So attacker now updates their belief that the real distribution is the real number is 1000. If the output is O2, then there is no information. It's probably equal to have this output. And if the output is O3, then attacker now believes that this orange distribution is the true output. But it's not belief. When I say belief, it's not 100 probability one. And the bounds of the update of the information of the attacker are given exactly by this graph, which represents the privacy loss, the graph of privacy loss random variable. So here, on the left, the update of the probability of the attacker will be at max this. The update of the probability here, we will trick an attacker here, but we will trick the attacker at max like this. And here we have this nice straight horizontal line. So this is the plot of privacy loss random variable, and we have nice bounds on it. And that's why the Laplace noise is so nice, because it has this beautiful shape. If it were Gaussian noise, for example, then it would have gone in here. And Gaussian noise can give you epsilon privacy, it can give you epsilon delta privacy because you have to cut the tail a little bit. But we don't focus on it, we focus on Laplace noise, and that's why it's nice. So I hope everything is, yes?
I have to ask
Yes.
silly questions again, sorry.
So sure.
So the initial thought was that we wanted to prevent Francois to be exposed in the future, right?
Yes.
So then there was the second concept of when you make a query to try to learn something on the database, right? Which was this. Okay, and now I don't understand to what this example with the blue number of people with blue eyes. It doesn't belong to the first category, right? It's you don't try to protect the individual here, right? So,
No, you can, for example, imagine that you have an auxiliary information that Michael Brown has blue eyes. You want to know whether Michael Brown is in the data set. And you know that in the data set there are at least 1,000 people with blue eyes, at least.
right. Okay.
And you have here in this quite generic example, you have quite precise information about your target. That Michael Brown has blue eyes, and also that there are at least 1,000 people in the data set. So you have already quite an information about that set. And even with this information, with this auxiliary information, adversary can't infer a lot.
So then I'm missing something because I mean in the initial definition there was nothing like this side information, right? So
I just mentioned it a little bit that in the very beginning that you can have any auxiliary information as an attacker. Differential privacy still preserves your privacy. But here, if we get rid of auxiliary information, you just want to see which data set is true. Consider it like this. So you have some assumption on the data set, and so you just no, maybe not this formula. Let's show this formula. So here you just have two hypotheses: whether data set is G1 or it is D2. That's the general formulation. And what does it mean that D equals D1 or D equals D2? Can have a lot of possible practical interpretations. It's just that, but the general formulation is that whether it's this data set or not. This hypothesis. Yes.
So if I understand correctly, it means that in some sense you want to protect yourself against the most pessimistic scenario.
Yes.
Where an attacker would know everything in the database except me, so he somehow managed to de-anonymize all the rest and just missing the information whether I am in the database or not, or whether I have cancer or whether I have criminal activities or blue eyes or whatever.
Exactly.
Okay.
So differential privacy, you can assume that attacker knows everything but him. But it shouldn't be the case. Maybe the attacker doesn't know anything at all about that.
It's kind of a worst case analysis
exactly.
in some sense.
It gives a guarantee on the worst case, but it also has nice property that you can treat your attacker by quantity exponential power epsilon. So here, okay, no more questions, and then a little bit more formality. You don't need to read the text, just the general we already know how the differential privacy is employed, but the idea is that you have some function, some very deterministic one. For example, number of people with blue eyes, or medical record, or something. Then differential private mechanism M will blur your data using some Laplacian noise. Laplacian noise shouldn't be auxiliary. It shouldn't be just arbitrary. it should depend on the properties of the data. And particularly, it depends on the maximum distance between the deterministic responses applied to our two datasets that we want to make it the same. What does it mean? I will explain on these two plots. So before that, in our previous example, we had these supposed to be quite close, right? Imagine that now it's not. Imagine that for example, imagine that the plots on the left, they depict the number of complaints an employee sends each year. And there is one guy who sends 100 complaints. So, and all the others, they are fine with their job and they send only one complaint. So basically the sheet of the datasets will be quite big, but the noise, if we add only like this, then it will be super easy for an attacker to distinguish between the two, because we have this one guy who sends a lot of them and then shifts the distribution to the right. So because of that, we will have to put much more noise on this data to make them look more similar. And this noise, so how much noise do you put? It depends exactly on the distance, the max, and the L1 norm of the deterministic outputs onto these two datasets. So imagine in my example that the dataset is a dataset without this guy, the prime is with this guy. So this quantity here will be 100, and then the Laplace noise will be the scale B, and guaranteed epsilon guarantee will be 100 divided by B. So if B is small, then epsilon will be large. Then you won't have a lot of privacy. If B is large, then epsilon will be smaller. So the closer two databases are, the simpler it is, the smaller noise you should add. But if we have this problem, then it's solved by this, and then you have a guarantee.
Yes, I have a question. Sorry if I'm anticipating or what you're about to say after, but so of course, if I make the same request many times and each time the result is randomized, I will begin to see the Laplace curve.
Exactly.
And of course, I will have the information that I want. So should it mean that when I make a request on the number of complaints, for example, the noise will be drawn at random once and for all, and then I will get always the same answer to that same query? So that's the first question. And the second question, which is related to that, so this would be an attack by asking several times the same question.
Yes, yes.
But you can also imagine another kind of attack by asking many different questions.
Yes.
So for example, if there is an employee for whom I know that he files a lot of complaints every year, but I also know that, I don't know, he has blue eyes and that this and this and this and this. By asking many questions, each time I will update my posterior, and in the end, I will have a very good information.
Exactly.
So how do you guarantee that the whole stuff is guarantees a good level of privacy?
Yes, that's a very good question. And that's what I mentioned briefly in the beginning when I said two major post-processing decomposition. So what you are describing here is called, at least in the tutorials, as leakage attack and tracking attack. Tracking attack is when you make the same query many times and you want just to draw the shape Laplace distributions. Exactly, you will be able to do that. If you make query a lot of times, then you will be able just to track, because the noise will be the same. You want to get, and the thing is that composition, so differential privacy doesn't guarantee you that you will avoid it, because it's impossible to avoid it. If you have possibility to make a lot of queries, then of course you will draw a distribution there. Unless you will have uniform distribution, but then it's meaningless.
You lose any.
Yes. And the thing is that composition gives you a rate with which your privacy protection is decreasing.
Okay.
And basically, if you have epsilon differential privacy for one query, making two queries will give you two epsilon differential pairs.
Yeah.
It's just from the property of exponential mechanism. And k queries will give you k epsilon pairs. So it increases, but you know the rate with which it increases. It's a tracking attack. Linkage attack is post-processing, basically, which means that we don't care, because you see, if even if the attacker knows everything in the database with some auxiliary information, still they can't infer anything about, I mean, they can infer something, but not a lot, up to epsilon, about our databases. And that basically is the defense against what you said, against linkage attacks. So when you make different queries, you compose some additional information that you gain from each query. Basically, what you said is, I think, is a combination of leakage and tracking attacks, but for leakage attacks, it's when you combine different knowledge about the target.
Okay.
You are defended up to epsilon. Against tracking attacks, you are defended by, but not for too long. There is only finite amount of queries that that will save your privacy. So after that, you will lose it. Yes.
So assume you take this additive noise same, right?
Yes.
Well, I'm not sure about the properties of the noise, but the Strong of large number, if you would reprocess the noise each time, resample the noise each time.
Yes.
The Strong law of large number.
Yes.
Would give you
yes.
the true thing.
Yes, exactly.
Right? And the speed that you allude to would be the speed in the, assume you have, I don't know, good properties, the speed of convergence of the empirical mean to
basically, yes.
Right?
Yes, exactly. Exactly.
So in that case, then the structure and the independence of the noise, if you repeat the thing and the database answers by resampling the noise, essentially, very, standard convergence theory.
Yes, exactly. It is the yes.
Okay. And this is why then you cannot guarantee anything.
Yes.
In the end, right?
Yes. Unfortunately, no. But in practice, if someone can, if your adversary can apply a strong law of large numbers, then it means that something is wrong with your with how you give queries, how you give responses, because it means that you gave too many responses, basically.
The database.
Yes.
You can control that to as many queries.
I think that you can, even if you cannot. Then yes, we know the rate we know the even amount of iterations after even amount of queries after which your private information will be leaked. So this is yes, you're completely right, but I think that I don't know, I'm not an expert of dictionary requests, but I just assume that if the adversary can make so many requests that they can apply law of large numbers, then it's a good idea to not allow them to.
In fact, it's also why I find the idea of decentralized the differential privacy, where the initial recording of the data is blurred, is way better, because you draw the noise once and for all, and then your queries are deterministic, and they always embed the same noise, so you cannot do anything with repetition of queries.
So that's very different.
Yeah. But in fact, it's the same formalism in the end, mathematically, but you
commute,
you have
to swap something. Randomization is the true data rather than the answer.
Yes, exactly. But the local privacy has some flaws. First, it's computationally expensive. It's more computationally expensive. Second, it gives you less useful data, a little bit. There are some boundaries in the literature. I've only heard about them. So I can't give you precise information on how much local privacy is worse or better in terms of privacy than centralized, but in terms of, you're right that it's a little better. And then we return to a little bit to the privacy loss random variable. I just wanted to, with our new notation that we seen on the previous slide, is just that privacy loss random variable that we introduced, whether we deduced from the definition of privacy loss, is basically the renewed divergence of order alpha equals infinity between the outputs of two mechanisms. It's just to give an intuition. So basically, privacy loss is the divergence between two databases, how much information you can infer from the response about one database about another database. So now to the application part. We have not that much time, but so I will make a lot of hand waving. Differential stochastic gradient descent. You want to, you have some data, training data, you want to make so the outcome of your SGD will be a parameter that you want to learn, and from then you want to make some predictions about something, and you want to not reveal so that this parameter that you learn doesn't reveal any information about the data itself. And then the idea would be to align the noise that you add at each iteration, and you add like at each iteration with the magnitude of the gradient that you compute. And that will satisfy the differential privacy assumptions, but it will satisfy epsilon delta differential privacy because here we can visualize. But the idea is basically just add some noise that depends on the data on each iteration, which is already stochastic gradient descent is already stochastic, clearly, and you just add a little bit more stochasticity here. What you do now from your parameters, it's hard to infer any particular private information that you want to consume about your training data. This is one way to employ differential privacy. This is the paper of 2016, how to employ differential privacy in learning. Another way to employ differential privacy, sorry, I forgot to say something about performance. We have high noise and privacy, medium noise and low noise. And clearly, when you add low noise, then it works better. But generalization works quite fine. I mean, you can generalize to your model quite a little bit better even sometimes, because basically intuitively that adding some stochasticity, and that's why in the sense to the training data allows you to work a little bit better. I mean, work nicely on the test performance because you're already. Yeah, because you're already on the training data, the more you obfuscate, but up to some scale, the more your algorithm is suitable then to the test data. I don't know if it makes sense, but it's the idea behind SGD beginning. And then another way to organize differential privacy is private aggregation of teacher ensembles. Here I will do some hand waving. You have data, you divide it into n data sets that are private labels. So this is the private data. You don't want to reveal the labels of these data sets. You don't want to reveal any information basically about this data set. Each data set is trained is used to train some model, which is called teacher. Then this combination of teachers is combined by randomized form. Basically, you add the sum of faults, add some noise, take the argument. So the randomized faulting mechanism. This noise here depends on the properties of the data, as is and the noise is oppression. And then this model is used to put labels on the already public data. So you label public data, which then in turn then this labeled public data can be used to train another model, whatever you want. And the differential privacy here arrives at this stage, Because the problem of differential privacy in practice is exactly what you said. You have only bounded amount of, so if you have even differentially private trained model, then you have only a finite number of predictions that you can make with this model. And this approach, it wastes this finite number of predictions on labeling the public data here, which then can be in turn used to teach another, which is a nice approach which combines some good ideas. So that's it for the applications. There are some properties that I wanted to say, but if we apply these to generalized adversarial networks, then just employing stochastic gradient, differential private stochastic gradient that I introduced is bad. It works quite poorly, doesn't give you any good results, even on miniest data sets, or the simplest data set possible. The variation of this strange differential private technique works nice. There's papers that show that. Here, the idea is the same. You just add a generator, and then you use your teacher to train generator. Oh no, to train discriminator. I don't know if you are familiar with GANs, but so basically,
at a high level.
That's it. Thank you a lot. I even made it on time.
Yeah, thank you very much. So there has been a lot of questions during the talk. We have time for a quick question if someone wants to ask. Is there a question in the room? Ludovic?
Yeah, just my curiosity. So I suppose that you applied this kind of the differential privacy for your work. Can you just explain very shortly how you use it?
Yes, I applied it in one of my papers. It's because I work on peer-to-peer electricity grids and trading on electricity grids. We applied not real differential pricing because it's a little bit too tight for controlling the distribution grid. But the idea was that we obfuscated some data that agents exchange between themselves. And our idea was that so what we relaxed is the assumption on the noise. Our idea was that they can control the noise that they add. And what we want to see, what is the spatial behavior? So how do they behave if they can control their noise on the data? And it showed that quite trivial result, honestly, saying that some agents lose from that, some agents gain because they can trick their peers. So that's how, but there are some other works where you apply real differential data or differential privacy on the electricity networks. So that why on electricity networks, on decentralized electricity networks. Why is it important? Because usually in electricity networks, you have to report your generation and demand to other agents, but you don't want to do that. You definitely don't want to report your demand because from your demand, from the track of your demand, you can immediately infer whether you are at home, how many people are there at home, etc., etc., etc. And that and from the generation, other agents can elevate the market power on you. So basically, you don't want to reveal this information. You add some noise, sometimes a lot. But the problem with electricity networks is that you should guarantee their operability because you can't allow the congestion. The price for congestion is high. You can allow a lot of things on there. So it has some issues. But it was me who used it like this. Usually it's used in a little different setting, like I said, Google, Apple, big corporations, a lot of data, just databases, etc. Yeah.
So there was this at one stage he said so there are plenty of principles blurring the database, blurring the answer, and perhaps this additional things that we discussed at one stage, which is only allowing grammar of questions.
Yes.
This way, does this way make sense? I mean, you could ask only successful questions on moments or things like that. So
that's a good question.
and so, is there a way to But there are some assumptions on the content of the database, right?
Yes.
To restrict through a proper language set of questions in such a way that this individual privacy be satisfied.
Good question. A really good question. I honestly don't know how exactly to do that. My not very educated guess would be that yes, it's possible. And if you restrict the possible questions that you can ask to the database, and then add some noise on top, then you will have better privacy guarantees, because now you can, yes, understand, yes, in one tutorial I encountered something like that. You can guarantee better privacy because of that. So if clients can ask on a particular set of questions, then epsilon will be smaller, because you need to control for less amount of unpredictable factors. Yes, yes, yes. But that's a good point. Hans is saying, up to which he also said you can restrict these questions so that still you can provide some information, right? Because if you have a big database with a lot of information, the query can be anything. People might want to know a lot of things. So it's a good topic. I don't know a lot about it.
Okay. So thank you again.
Thank you.